In this video, we will investigate several more examples of finding the volume of a solid using the method of shells. So, just as a reminder, this is the shell method. So the idea is that if f of x is a non-negative function for values of x between a and b, so we're thinking y equals f of x from a to b, and if we take that region enclosed underneath our function and we rotate around the y-axis to form a solid revolution, if we would like to calculate its volume, it's given by the following integral. The definite integral over how the x values vary, a to b. What we integrate is 2 pi x f of x. And let's remember exactly what the x and the f of x represent in the situation. We take our area, we break it up into a bunch of little rectangles, and we take each rectangle and we rotate it around the y-axis to form the so-called cylindrical shell. And in this cylindrical shell, we're thinking of the x as representing the radius, and we're thinking of the function value, f of x, as representing the height. So really, we draw a general cylindrical shell, and the x is representing its radius, and the f of x is representing its height. So let's put this to work. Determine the volume of the solid obtained by revolving the region bounded by y equals x squared, y equals 2 minus x squared, and x equals 0 in the first quadrant about the y-axis. Okay, so we're just dealing with what's in the first quadrant. We have y equals x squared, this kind of standard parabola opening upward. Then we have y equals 2 minus x squared. So it's going to have a vertex at 2 on the y-axis, and it's a quadratic opening downward. So we see this nice enclosed region. So once again, the parabola opening upward is y equals x squared, and the parabola opening downward is y equals 2 minus x squared. And we would like to find the volume of the solid obtained when we take this region and we rotate it about the y-axis. So we're going to use the method of cylindrical shells. One question you might be wondering is, can I use the washer method? Well, you could use the washer method, but what you would have to do then is think about it as two separate solids. You would first think about the volume you get from rotating this bottom part around the y-axis, and then another second volume calculation. The reason being is when you would think about the washer you formed, actually a disc in this case, the radius that you used would be different below as it would above. So cylindrical shells is going to be the way to go. So we cut this up into some vertical rectangles, and we rotate it around the y-axis. And I've illustrated here a typical cylindrical shell. So the first thing we're going to have to do is figure out how our x values vary. So we see one point of intersection occurring at, well, the starting point being 0, and then we need to figure out the point of intersection. So we set the two curves equal to each other. So x squared equals 2 minus x squared. So 0 equals 2 minus 2x squared. So 0 equals 2 times 1 minus x squared. So x equals plus or minus 1. And for us, it's the positive one that we are interested in. So the volume is going to equal the definite integral from 0 to 1, 2 pi something, something. So recall the first something is representing the radius of the cylindrical shell. In this case, the radius is simply x. Now you might be wondering, when will the radius not be x? Well, typically when you're rotating around a line that is not the y-axis. Here it is x. And then the next blank is the height. So notice in this case our height's a bit different because it's enclosed between two curves. So for the height, what we'd have to do is think about the top curve, 2 minus x squared, and we subtract away from that the lower curve. So our height is 2 minus 2x squared. And now that we have this set up, evaluating the integral turns out to be the old part of the problem. So we have a 2 pi that pulls out front, then it's a definite integral from 0 to 1 of 2x minus 2x cubed. Anti-differentiate term by term, x squared minus 2/4, which is 1/2, x to the 4th from 1 to 0. We plug in a 1, which would be 1 minus 1/2, minus sign, we plug in 0. So the value of the volume of this solid is simply pi. So let's look at one more example. And in this example, we're going to look at something slightly different. Not only are we not going to revolve about the y-axis, we're going to revolve around a horizontal line different than the x-axis. So we want to take the region bounded by the curve x equals y squared. So that's a parabola opening to the right with vertex at the origin. Y equals 2. X equals y squared. And x equals 0. Note x equals 0 is simply the y-axis. So we see this nice region enclosed. And what we would like to do is form the solid by revolving that region around the line y equals 2. Now, you could use the method of washers here just as easily as the method of cylindrical shells, but I want to use the method of cylindrical shells to illustrate how this works. So we are going to do the same thing, except now since we're rotating around a horizontal line, we're going to set up our integral in terms of y values. So that volume is going to be the definite integral over how the y values in our region vary. Well, we vary from y equals 0 up to y equals 2. And what we need to integrate is going to be 2 pi something something, where the first something, remember, is going to be a radius of our typical shell. The second something is going to be the height of that typical shell. So if we draw a typical shell, we're now going to want to break this up into horizontal pieces, and then we're going to rotate that piece around the line y equals 2. So looking at the radius of this, if we have a y value where we've drawn that rectangle, the radius is going to be 2 minus y. And the height is simply going to be given by the function value, y squared. So a bit different than we saw in our previous example, because the radius was something different than, say, just the variable x or y. And the key to indicating what that radius is to draw the typical shell and look in your picture and think, what is the radius? In this case, the distance from y to the line we are rotating about, 2. So let's evaluate. 2 pi pulls out front. We have the definite integral from 0 to 2. And we're going to take the y squared and distribute it through. So that'll be 2y squared minus y cubed. And then we anti-differentiate term by term. So the 2 pi is hanging around out front, and we'll have 2/3 y cubed minus 1/4 y to the 4th, all from 2 to 0. So we plug in 2, we put a minus sign, we plug in 0. So 2 cubed is 8 times 2 is 16. 2 to the 4th is 16 over 4. And when we plug in 0, we get back 0. So 2 pi times 16/3, and 16 over 4 is 4. So this is going to end up being 2 pi times 4/3, which is 8 pi over 3.